So let's sum up what we've seen about the performance of these different ways of searching for function optima. We've identified a number of techniques up to this point. We can say that if your problem is small, however it's formulated, then brute force may be a good answer. It just has to do with the size of the search space that you have to consider. And again, the nice thing about brute force is that it guarantees that you find the true optimal answer. If your problem is convex, then hill climbing or greedy algorithms work very well. And we saw that in connection with the basin hopping algorithm. If your problem is bumpy and it's discrete, a random walk performs very well. If it's bumpy and it's continuous, then basin hopping is probably your best way to just handle the problem entirely. It'll look in a lot of places. It's a little bit more computationally expensive, but it's a nice one-stop shop for finding those maxima or minima. Real-world problems can sometimes be phrased in such a way that you're finding an optimum, but frequently the available data are too sparse and the nature of the configuration space is too fuzzy to permit a clean statement of the problem. In these cases, it's often necessary to either break the problem into smaller pieces which can be optimized, or to assume or model unknown parts of your data set. Optimization is a very broad field, and it's been the focus of much applied mathematical research in the last century. By securing an understanding of the basic contours of the problem and the solution approaches that we've seen so far, you'll be able to identify the techniques and applications which underlie your standard computational toolkit moving forward as a scientist or engineer.